हो हो.
मोहिते सर, लिंक सगळ्यांना गेलेली आहे.
ओके, लिंक गेलेली, सुरू पण झालंय.
आणि एकदा आपलं सुरू झालं, इंट्रोडक्शन झाल्यानंतर की तुमच्या पण सगळेजणच आपण माईक ऑफ करूया.
येस येस
सर, एकदा चेक करा बरं, मी केलं युट्यूब स्टार्ट.
हा, दिसतंय, व्यवस्थित दिसतंय. येस
हो सर, आवाज येतोय का बघा बरं.
येतोय आवाज व्यवस्थित.
सर किती वेळ येतोय?
येतोय लगेचच, म्हणजे आता कसं कळेल?
हा चालेल, 5 सेकंद पण झालं.
मोहिते सर, 20 सेकंदांनी बरोबर सरांचा इंट्रो सुरू करा.
हो हो.
येस
चालेल सर, मी ऑफ वर जातोय, म्हणजे माईक बंद करतो.
हा हा, ठीक.
ओके.
Good morning all. Today is the second day for the webinar on hydraulic modeling of water supply and sewerage networks using Bentley Water James and Sewer James Connect Edition. Speaker Mr. Tanay Kulkarni, Master of Civil Engineering in Hydraulics. He is also certified Big Data trainer from MIT Technology USA. He is highly experienced water profession with a good record of training thousands of water practitioners and engineers of the globe and helping them to tackle their unique challenges using hydraulic modeling technologies. Mr. Tanay Kulkarni previously works with Bentley System, where he leads as water solutions consultant and was responsible for Asia Pacific and Middle East region. Faculty specialize in water mechanics, hydropower engineering, and surge analysis, including big data and hydraulic modeling using GIS. I request Mr. Tanay Kulkarni to start the session of the webinar. Thank you.
Thank you, Dr. Mohite sir, and welcome all to the second day of this webinar series. The topic of today's webinar is hydraulic modeling of sewerage networks using Sewer James. Let me quickly introduce about my startup. We are DTK Hydronet Solutions, founded in 2016. We are the winner of the prestigious Year in Infrastructure Award back in 2018 at London, UK. We are a team of water engineers and hydraulic modelers having strong expertise in irrigation engineering consultancy. We have pioneered hydraulic modeling as a service in India, where we help contractors and utilities analyze and maintain their hydraulic models and take operational decisions based on hydraulic models. We also have expertise in water, wastewater utility engineering, and GIS consultancy and services. We are also Bentley's technology partner and Bentley's training partner for India. The agenda of today's seminar is going to be introduction. We are going to start with introduction of sewerage networks and network design engineering workflow. We are also going to see how to build a working hydraulic model of a sewer network. And we are going to look at the the top most frequently used tools in Sewerage. And then I'm going to quickly demonstrate Sewerage to all of you. So let us start with introduction of sewerage networks. Yesterday we saw how typical municipal water cycle looks like, where we saw that civilizations are settled on the back of rivers, and here are two cities that are settled on the bank of this river. So water infrastructure considers intake of raw water, treatment, supply of this treated water to consumers all across the city. These consumers consume water and then they flush. The wastewater thus created is collected using sanitary wastewater infrastructure, and it is collected at STP, sewage treatment plant, where the wastewater is treated, and this treated wastewater is then disposed of back into the river. And this water is then considered as an intake raw water by the city, which is downstream of the same river. Now we'll take a look at typical water supply scheme. We saw what water supply schemes look like, and what is the how the skeleton view of a water supply scheme is. Today we are going to see how a typical sewerage scheme looks like. Now, once we supply water, it's also the utility's responsibility to collect this consumed water in the form of wastewater. We collect this water and we treat this water, and we have to reuse it or dispose it back in the source. So here you have a schematic view of a typical sewerage scheme, where you have different lateral mains, sewer lines, which are collecting water under gravity, wastewater under gravity, and then these laterals are to sewer mains. Then the sewer mains are either connected to a wet well chamber, where this wastewater is collected in a tank and pumped to a higher location on a trunk sewer line, or the sewer mains are directly connected to trunk sewer lines, from where the water is collected at the end at the treatment plant. So we have different combinations of hydraulic calculations which can be considered while analyzing and modeling a sanitary sewer network. For instance, in this particular case only, we have pressurized hydraulics as well as open channel hydraulics. Right? So all this wastewater is collected with the virtue of the potential energy that is available in the water, and that also means that we are collecting it under gravity. Once this is collected, and if we have some topographical challenges that water cannot be lifted, so in that case we induce additional energy with the virtue of pumps, and we lift this wastewater from these wet wells to a higher point in the trunk main. Now we are going to see, yesterday also we saw that it all begins with surveying. So we have a master orthomosaic image from which we can create a digital terrain model. We again lay sewerage networks along the roads, right? So therefore we collect spot elevations along the roads, and using these spot elevations, we generate vector contour model. So this is how we develop geodatabase for a sanitary sewerage infrastructure project, where we collect all the data that is available, data such as, if you have an aerial imagery, then we digitize different parcels and land use, land cover maps, right? And then we have landmarks and building layer. Then we have contour, that is terrain layer. And we assign attributes, that is we generate metadata of all these different vector data. And thus we create a georeferenced geodatabase. And once all this data is developed, then comes the process of hydraulic modeling. Now, we yesterday saw what a hydraulic model is. Again, I would like to repeat. A hydraulic model is a mathematical representation of your real sewerage or water supply infrastructure. So it's a mathematical representation, and this representation consumes different types of equations, and calculations are being modeled so that it gives you hydraulic information as a form of result. Now, what kind of hydraulic information would a sanitary sewer network give us? It gives me what is the depth of water. For conduits, it gives me what is the velocity of wastewater flowing through those conduits, right? Is it maintaining the self-cleansing velocity criteria that the CPHEO mentions, or is it violating the maximum scoring velocity? Is it going beyond that? So we can have an understanding of velocity, we can have an understanding of discharges, and then we can also have an understanding of this D by D, that is depth of water inside the conduit divided by the diameter of that conduit. So we can have these different properties as part of results that are generated once the hydraulic model is computed. Also, for manholes, we can have an understanding that which manhole is contributing how much sanitary wastewater load on the system. Again, in CPHEO, it mentions that these peak factors needs to be contributory in nature. So as we approach the STP, the peak factor on individual manholes keeps on increasing depending on how much population is contributing to every manhole as we approach the STP. So we can set that, and thus we can generate a hydraulic model. Once we generate a hydraulic model, we can take decisions like either we are designing the network entirely new network, we can design it, we can see how the operations are functioning, we can analyze the network over different worst conditions, like if there is storm water which is being entering our sanitary wastewater pipelines. If that is the case, whether that would cause any kind of overflows in the network. So these kind of studies can be done on hydraulic models, and this helps the utility, that is the water board, or the municipal corporation, to have an understanding of what is actually happening beneath the ground. So let us take a look at the workflow for creating a working hydraulic model of sanitary sewerage network. So we start by developing and building this data model. We can develop that model in GIS, which is what I would prefer, or else you can have some CAD file, CAD information, and you can have some Excel information, right? And thus we develop this data model. We have to keep all the data ready for development of a hydraulic model. With this data, we generate a hydraulic model, we construct a hydraulic model, we enter all the physical properties of the elements of hydraulic model. For example, if I have an existing pump in the network, right, sanitary pump station, so what is the pump characteristic curves, right? So if that is an existing pump, I'll have to gather all that data, and I'll have to enter that physical properties of pump, for instance, in the hydraulic model. Then we start allocating the sanitary loads to every manhole. In India, it can most of the utilities calculate this using some kind of Excel, or you can also use GIS maps and polygons to understand what is the contributing population on every manhole, right? Once we understand what is the contributing population on every manhole, we understand what would be the sanitary load on those manholes. Then we compute the hydraulic model, or we design the hydraulic model. If it's an existing network, we would be interested, before we plan the expansion of that network, we would be interested in what is happening presently today with the existing infrastructure that we have. right? And then on the basis of that understanding, we can take intelligent decisions like which are those pipes that needs replacement, right? Which is the area that would be contributing higher loads or more loads on the system over a period of 30 years, next 30 years. And in this process, fundamentally, the software is always there to help us. But most important thing is that the modeler or the designer or the design team needs to have a vision, right? For example, you might face a challenge like in the case of Pune city, right? We have this Hinjewadi, which was not foreseen development, right? It was not a planned development. And all of a sudden, in a matter of 10 years, a huge sector is developed, right? And we know it today, we call it as Hinjewadi phase 1, phase 2, phase 3. So all these additional loads have to be envisioned before you actually start developing a hydraulic model and designing a sewerage system. And you will find all these development programs and development plans projected for a city in the city's city development plans. All right. Once we compute this hydraulic model, once we compute this hydraulic information, we then interpret the results. Now, you also have to have an understanding. See, the software works on the primary function, data in, data out. That is, whatever I input, I'll get some output, right? Because it calculates and it generates output. However, if the data is manipulated, if the data is compromised, the software would only give compromised outputs, right? So interpretation of results is also an important parameter when we are handling or developing or using a software for hydraulic modeling. We'll go to the next slide. So there are, so I'm going to introduce 2 to 3 different softwares, and then we are going to come to Sewerage, because these 2 to 3 softwares combine together to form Sewerage. So Sewerage essentially is a superset, which is a combined combination of 3 different softwares. The first software is SewerCAD. Now, SewerCAD is a sanitary sewer design modeling software in which you can analyze, model, and design your sanitary sewer networks. All right. And you can have extended period simulation as well as steady state simulation analysis in this software. It can also handle pressurized as well as gravity systems, like I showed in the first couple of slides, where you collect water under gravity up to a certain point in the network, and then you pump the water either directly to the STP or to some high elevation from where water would flow under gravity, right? So, and you can use SewerCAD to automate the design of pipelines and inlets. It will also be helpful for you to understand how and what should be the manhole's invert levels, right? What are the optimum invert levels of every manhole, right? And whether it's possible for us to practically have those invert levels in the network, because it depends on so many other factors. For example, to give you an example, it also depends on the what is the kind of substrata that we have, right? It depends on the type of rocks, right, that we have beneath the ground. So it depends on multiple factors, but it gives me an idea whether I should go for that particular invert level or I have to go with some other invert level. So this primary design can be obtained with the use of SewerCAD. The next software is StormCAD. Now, StormCAD is a software for storm sewer modeling and design. Now, when I say storm sewer, all the water infrastructure that you have in the city, you can model, analyze, and design that infrastructure using this particular software. Now, mind you, sanitary sewer hydraulics is different than storm sewer hydraulics. The fundamental difference is sanitary sewer, the loads are being contributed by human population. However, for storm infrastructure, the water load on the system is being calculated by the rainfall events, right? And it also depends on what kind of return period are you dealing with, right? So this uses the the popular equation, the formula, rational formula, to analyze and understand the discharges through pipes, and it can be used as standalone, and it can also be integrated entirely with AutoCAD, and it offers quick model building tools. It is easy to use, layout, and so on and so forth. However, this tool can also be used for automated design of storm sewer networks, right? So this is another tool that I want to introduce. The third tool that is Civil Storm. Now, Civil Storm uses dynamic wave modeling, dynamic wave routing, and it offers fully dynamic stormwater analysis and optimization. Now, when I say dynamic wave routing, most of you might know this popular equation, St. Venant's equation. It starts using St. Venant's equation for dynamic wave modeling. For example, if there is a rainfall event at particular location in the network, how that surge, the water will be transported from one part to another. And you can analyze multiple rainfall events of different intensities at different locations of the city. Now, this is really important for cities like Mumbai, right, which suffers stormwater crisis almost every alternate. Right, you will find manholes being overflown, then you will find the stormwater infrastructure inadequate, right? And you have to understand whether if it rains heavily in Parel, how is that affecting in Worli, right? In other part of the network, because this goes across up to Worli storm. This is an example, right? So you can use Civil Storm to understand dynamic behavior of rainfall and its impact on the stormwater infrastructure. Now, these are the three different software using different equations, having different hydraulic mechanisms working behind it. When I combine all these three softwares, that is StormCAD, SewerCAD, and Civil Storm, when I combine these softwares and I bundle it in one software, that software is called as Sewerage. Now, as I told you yesterday, this GEMS, GEMS, it stands for Geospatial Environmental Modeling Software. So this offers complete integration with GIS application, which is ArcGIS. At the same time, it offers complete integration with AutoCAD and MicroStation. So CADing as well as GIS application, right? So when I say that it offers complete integration with GIS, I intend to say that if I open ArcGIS, I can use all the features and functionalities of ArcGIS, and on top of it, I can integrate ArcGIS with Sewerage. So with all the features and functionalities of ArcGIS, I can use all the features and functionalities of Sewerage, is all these three software right within ArcGIS. So everything will look like ArcGIS, but you'll have an add-on feature of Sewerage functionalities right within ArcGIS. The same is true for AutoCAD. So Sewerage also completely integrates with AutoCAD. So all the features that you'd be looking at would be available right inside AutoCAD. What are the industry applications of Sewerage? So you can use this for municipal underground sanitary sewer network, sewerage schemes. You can use it for municipal storm sewer schemes, right? You can understand the pumping operations of different, local pump stations, right? And it can also be used in a very controlled environment, like in the case of an industrial property or a plant, right? Industrial, this oil refineries and so on and so forth, where it is really controlled environment. You'll find controlled environment, and they're really worried about every infrastructure, aspect of the plant. So these are the different applications where you can use this software. So SewerGems is a comprehensive decision support tool for modeling, analyzing, designing combined wastewater as well as stormwater networks of a sanitary or storm sewerage scheme. Now let us take a look at the most frequently used tools inside SewerGems. Again, like WaterGems, these are the top 3 tools that will be helping you save a huge amount of time. The name of the tools are Model Builder, T-Rex, and Load Builder. Now this is the workflow for model building, model development. You need to have GIS data. If you don't have GIS data, you can use CAD data, Excel data. You can combine this database. So you need to have database, and then you have to use Model Builder to generate a model with all the data which is available. Okay, you can use Model Builder to import Excel. You can use Model Builder to import CAD data. You can use the same tool for importing GIS data. Once you develop or create a fundamental or a basic hydraulic model of your sewerage network, then you use Load Builder to import sanitary load conditions and assign those load conditions or those loads to individual manholes. So this is where you can use Load Builder to automate this process, because as all of you know that we have to consider a manhole for inspection and maintenance purposes at every 30 meters of the pipe length. Now, if I consider this, I would end up having lakhs of manholes, literally thousands of manholes for a city of like Pune, right? So it would be really tremendously difficult for a modeler or for an engineer to assign sanitary loads for each and every manholes, right? So this Load Builder will automate the entire process, and in no time it will assign and distribute sanitary load to all the manholes across the network. So this is the second tool that is going to save you a lot of time. The third tool is elevations play an important role when it comes to sewerage infrastructure. There are 2 aspects of it behind it. First is there is very little or negligible revenue which is actually generated out of a sewerage infrastructure, right? Unlike other countries like Australia or US, you do not get sanitary bills every month, but we do get water bills every month, right? Water bill you do get. So the government, the utility generates very little amount of revenue out of the investment that is that they have to do for development of sanitary infrastructure, sanitary sewerage infrastructure. So the primary focus is to save operational cost or reduce the operational cost of the scheme. For that, most of the utilities depend on gravity flow as compared to pumping flow. So they'll collect water under gravity, right? The next aspect is, since these systems are under gravity, you need to maintain the directional ground level slope, right? Ground slope as you approach the STP, right? So elevations play an important role, and these elevations need to be assigned to every manhole. And like I told you, there would be tens of thousands of manholes in your network, and individual assignment of elevation may become a tedious job for you. Therefore, Bentley has developed another tool which is called as T-Rex. Now, T-Rex stands for terrain extraction, and it helps the modeler to automate the extraction of elevations from all the elevation data that we have. For example, what kind of data do we typically have? Data like contours, right? It may be CAD contour or it may be GIS contour. then digital terrain model, right? DTM, or digital surface model, right? Or digital elevation model, right? So data, elevation data may come in different formats. In different, it may also be a simple total station file, CSV file, where you have northing, easting, and Z coordinates for every station point. And using that, you'll have to interpolate and develop contours in another application like GIS or AutoCAD. Once this data is generated, you'll then use this tool, T-Rex, to automate the process of elevation assignments to all the elements, all the nodes of your network, like pumps, wet wells, junctions, that is manholes, so on and so forth. All right. Once all this data is loaded on the hydraulic model and the model is cleaned, the model then becomes runnable. That is, it is okay. It becomes error-free. It becomes okay to be computed. Now, if I have an existing network, I can use this hydraulic model for calibration studies. If I want to completely develop a new infrastructure, then I can use this hydraulic model for design purposes. All right. So there are some constraints to which the design is subjected to. Constraints like I should not be having, the depth of invert of manhole should not go below a certain elevation because I want to save cost of excavation. Constraint number one. Constraint number two can be I want to achieve a minimum value of velocity so as to ensure that I end up having minimum maintenance activities, right? That which is velocity, right? So velocity becomes your constraint number three. And in order to maintain velocity and cover, there comes the third constraint, which is slope of the pipeline below the ground, right? So these are the three constraints with which which can be subjected to your design, and the software would automatically determine the design parameters. Now, what are the design parameters for a sanitary sewerage network? The design parameters would be the invert elevation of every manhole and the diameters of every conduit, right? So the software, based on these constraints, the software will optimize diameters and invert levels, and it will give that as a result. Now, as a water engineer myself, I would recommend you to use this tool to automatically develop a primary model, right? Primary design. But I would want you individually to put your brain, your ideas, your inputs, design inputs to that thus automatically created hydraulic model. Do not go with a Sewerage generated hydraulic model to the utility, because that is a software generated model. We need to have a model which is project specific, which understand what is the subground strata, right? Geology. And then we need to understand so there are so many understandings of a project. We need to have all these inputs, and we need to have a customized design. So I want I would have me doing or modifying or customizing the automated design before I go to the utility and submit it. So this is the model workflow. I have already explained what model builder is. So model builder will consume all the possible data source. It can be a simple Excel file, or it can be a CAD file, and it will consume that to create a Sewerage sanitary sewer hydraulic model. Then comes T-Rex. As I explained you what T-Rex is. T-Rex stands for terrain extractor, right? And it extracts digital terrain information from your database and assign it to your hydraulic model. Then comes the load assignment. Now, load assignment is really important because you have population parcel data, right? So for example, you have population wards, that is ward-wise population. For every ward, there would be census-based population, right? So we have to project this population for the next 25-30 years, and that projected population will be contributing some sanitary wastewater, and that wastewater should be collected through our infrastructure, and our infrastructure should be designed accordingly. So how do I understand what would be the sanitary load being collected on every manhole? I cannot go, I cannot have a house to house survey done that, okay, you are connected to this manhole, you are connected to that manhole. So for this, we need to have a logic. Now the logic that I'm presenting here is load assignment based on population data. So I have population based walled boundaries. I project this population for the next 30 years, and then I calculate what is the population density of every ward. Right? Now with that information, I also need to understand what is the area that a manhole will be catering to, that a manhole will be responsible for collection of wastewater. So to understand that area, we can develop Thiessen's polygon. Now, like I told you, we need to automate this process because I cannot keep on developing Thiessen's polygon. So there are some tools which would help you automate many of the workflow things so that you can develop and assign and create a hydraulic model quickly and efficiently. Now, this is the Thiessen's polygon, as you can see on your screen. What we are going to do is we are going to understand, the software is going to understand what is the area of that Thiessen's polygon, and then it is going to overlap that Thiessen's polygon with the ward data. Now, once this overlap happens, the Thiessen's polygon might lie in two different wards, having two different ward-wise population densities, right? So this is the case that I'm showing you on the screen, where I have area A of Thiessen's polygon falling under ward 11 and area B of that same Thiessen's polygon falling under ward 12, right? So what we want to do is we want to understand what is the total population in area A and what is the total population in area B, so that then I can multiply it with my standard load and I can understand what is the contributing discharge at manhole 1. So here, as you can see on the right of your screen, I have area A multiplied by population density, which would subsequently give me the population of area A and population of area B. When I combine these populations, I get total population contributing to manhole 1. And when I multiply that population with my standard load, which is 108 liters per capita per day, where does this 108 come from? It comes from an assumption that whatever water I'm supplying to the consumer, 80% will be flushed inside the sanitary wastewater network. So 135 is the average that we supply, and 80% of 135 becomes 108. That is what we are going to collect. All right. So this is how we calculate loads on every manhole. However, if you have, thousands of manhole, would you be doing the same thing manually for every manhole? No. So therefore, you have different tools inside. So different tools like Thiessen's polygon and load builder, which when combined can save you a lot of time. All right. So you can see on the screen, this is why we need load builder, and load builder can consume different types of data. For example, it can be used for, like I explained you, it can consume the population data from walled boundaries, and it can allocate that population data to individual manholes with the logic that I explained you previously. Then I am going to come to 1-minute demonstration of Sewer Gems. So let me go to Sewer Gems. So this is the standard graphical user interface of standalone version of Sewer Gems. This is how it looks like. And if you observe, it resembles very precisely with other Microsoft applications like Microsoft Office, for instance. So you'll find all these options right within Microsoft Word as well. So the graphical user interface is really sorted. It is quite easy for a user to navigate through different operations, different functions that the software offers. So here you can see a sanitary wastewater network. Now the connectivity logic is a node, a link will be connected to one node on either side of it. So node link, node connectivity logic will be used. So as you can see, the nodes here are different manholes and the links are different conduits. There are pipes, right? So, and there are two outfalls over here. And this wastewater being collected from this particular region will be collected in these two outfalls. So you may have different outfalls. So if you can see over here, it has got a curved arrow. If you see here, it has got a curved arrow, this pipe 13. So what it means is this is a diversion link. So if the level, discharge in pipe 5 increases or goes beyond a certain value, all the additional discharge will be diverted in P13 and it will be diverted to another outfall. Outfall essentially is a collection chamber. It can be a sewerage treatment plant or it can be a wet well. All right. So you can model different complex networks like this. You can also combine it with pressurized hydraulics. Like in this case, manhole 12 is contributing sanitary load under gravity through pipe P12, which is being collected at wet well 1, this WW1. So this is a tank, a well, where all the wastewater will be collected from manhole 12 under gravity. But because of topographical differences, I want to lift this wastewater and discharge it to manhole number 3. So I can combine this gravity flow hydraulics with pressure hydraulics. Like you can see, I can have pumps and pipes running full pressurized pipes, and I can discharge water to manhole 3. From manhole 3, again the water will be collected under gravity to outfall 1. So you can go ahead and compute this network and you can generate results out of it. I have already shown what kind of results can be generated, right? And then you can do some really interesting stuff, like you can understand what is the temporal behavior of your sanitary wastewater network over a period of time, right? So that that means that you can do extended period simulations on your hydraulic model. Now, what does an extended period simulation means? See, if I color code this network on the basis of flow, so I'm going to go ahead and color code this network on the basis of flow, right? So you have different colors indicating different discharges through the pipes. Okay, so this is where you have the color code, and presently all the lines or all the conduits are green in color. That is, the discharge is less than 67 liters per second. Now, if the discharge is fluctuating over a period of time, I can then analyze what is the temporal behavior of the network, how the pipes are filling, right? What is the how the D by T ratio is fluctuating throughout 24 hours of the day. So I can do EPS analysis, and then I can have a time-based visualization of the network, as you can see over here. So here, after every 20 minutes, it is going to show you how the network is behaving, which manholes are contributing more water. Are there any manholes which are overflowing? If so, how many hours would those manholes be overflowing? So that you can take preventive measures, right? Or you can be ready for that emergency well ahead in time. So you can train your operators and your maintainers well ahead in time by simulating a worst case situation on a hydraulic model, and make them ready for the emergency situation well ahead in time, right? So you can use such hydraulic models for modeling such situations, right? So this is one of the application or use case of sanitary wastewater. Of course, I can consider that this is a completely new system and I don't know what the diameters are. I also don't know what should be the manhole invert levels, and I can use the same software to design. The only difference would be my objective of using hydraulic model would be different. All right. So this is how you use a hydraulic model. You can also generate profiles. So here we have a profile, right, of manhole 12 till outflow, outfall, and then you can animate this profile and understand when the pump should start, when the pump should stop, right? So if I go ahead and hit this play button, so it will help me how the water levels in the wet well, that is the collection chamber, are fluctuating over a period of time, and when the pumps are starting, when the pumps are tripping, right? So you can do different kind of control. You can subject your hydraulic model to different kind of controls, and you can evaluate different options of controlling your system, right? So this is how Sewerage looks like. So this is where I would stop this 1 minute demonstration. I have explained it in all the possible details that is possible for this session, and then I'll come back to my presentation. And I would like to thank each one of you for sparing your time. And I would also insist and request you to go on this page, www.dtkhydronet.com/waterwisdom, to read the technical articles, everything related about water infrastructure, infrastructure, stormwater infrastructure. And I hope that you will find these articles interesting. If you find so, please feel free to share those on social media like LinkedIn, and please follow us on LinkedIn. With that, I would like to thank each one of you for giving your time. I would like to thank COEP and all the organizers for giving an opportunity to speak at this 2-day webinar on water gems and sewer gems for water supply and sanitary wastewater projects and schemes for India. Thank you so much. Organizers, if you have any questions, if you could collect any questions, and if our viewers have any questions, we can address those. I think we still have 15 minutes, so we can have a small round of discussion if it's possible.
Hello, is there any question related to this? One question is there.
Yes, sir.
Swanand Sathe, can pumps be also designed in both?
Okay, that question. So, hydraulic design of a pump. So the question by Mr. Sathe is, can pumps be designed? So there are two components of a pump: a mechanical design of a pump and a hydraulic design of a pump. So hydraulic design, you can understand how the pump is behaving. What are the pump performance curves? You can generate system head curves. You can compare it with your pump curve, and you can have an understanding whether the pump is operating at a good or greater efficiency, or can the efficiency be improved. Those kinds of understanding designs can be done with the help of this software. However, mechanical components of the pump cannot be designed because it's a hydraulic modeling software. I hope that answers Mr. Sathe's question.
One more question is there from Ajay Ungole.
Yes.
How could we manage flow? Suppose my pipe diameter is 450. What will be the slope?
I'm not sure whether I got that question.
He's asking, how could we manage slope? Suppose pipe diameter is 450, what will be the slope?
So if the pipe diameter is 450 and what should be the slope? So it also depends on what kind of discharge are we talking about in that 450 diameter pipe. It also depends on what is the incoming inward elevation, right? And it also depends upon what is the end elevation of the outfall to which I have to. So there are so many aspects to it. I cannot think of an answer to give you right away with such a limited information. But yes, the software will give you an understanding or a hint. But I think that we should. It's our responsibility that we should have our inputs after the design is given by the software. So it depends on many aspects. I don't think that it is possible for me to give you a vague answer for this question.
Okay, thank you, Tanay Kulkarni, for a wonderful presentation. I received a response from various participants. Thanks a lot for your valuable information, new ideas related to the water distribution network and sewer network design. Thank you. Thanks a lot.
Thanks for the opportunity. Thanks for being patient.
Yes.
Thank you.
I also thank Dr. Vishal Halsure sir and Amay for their help to manage these technical difficulties which we face in a day one. Okay. Thank you. Thanks a lot.
Welcome, sir.
Thank you.
Sir. Yeah.
Okay. Okay.
Thank you. Thank you, Tanay sir. Thank you, Mohit sir. Thank you, Sunil sir. Amay, stop broadcasting.